Hello and welcome to this presentation on bearing failure analysis. We're going to talk about why do bearings fail, how to detect bearing defects, and how to extend the life of rolling element bearings. My name is Jason Tranter, the founder and managing director of Mobius Institute. Rolling element bearings are critically important in industry, and of course we need to keep them turning. Rolling element bearings are designed to run for a very long time. It's all a question of how they are treated and therefore how much life you actually get out of those bearings. They're in all sorts of machines, as you well know, and there are lots of ways that we can monitor them and care for them. So the challenge is, we know that they can fail, we know that they do fail, so the question is, what can we do about it? So, number one, we can practice breakdown maintenance. We can just let the machine fail without taking any preemptive action. Of course, if we hear something audibly before it fails, we can take action to stop a catastrophic failure, but still we're very much reacting to the failure of the machine. We can perform preventive maintenance to try and prevent them from failing, replacing them on a routine basis and taking other actions that we believe will stop them from failing. Of course, unfortunately, many studies have shown that most preventive maintenance practices don't actually prevent bearings from failing. In fact, in many cases, you're increasing the likelihood of the bearing failing. And then, of course, we can use predictive maintenance. We can use techniques that are better than just our sense of hearing to detect whether a bearing is beginning to fail and take action. Of course, this is really just a form of reactive maintenance. It's just that we're reacting to the problem much earlier. And if we do it properly, of course, we get a nice early warning that a problem is developing, and we can then plan accordingly. But finally, we can look at proactive maintenance, and that is taking action that will reduce the likelihood of a bearing failing. We can balance the machine, improve the lubricant, take care of our installation procedures and so on to reduce the risk of failure. So the question is, we have different strategies, so what can go wrong? Let's have a look at why bearings fail in the first place. I think it's fair to say that unless you understand why they fail, it's pretty hard to prevent those root causes of failure. Now, the numbers presented here were from a study by SKF some time ago. You may see different studies with slightly different figures, but basically there are four main areas four main causes of bearing failure. One of the key numbers, which again you may see slightly different numbers reported in different places, but a vast majority of bearings, rolling element bearings, do not reach their design lifetime. So let's look at the first cause, fatigue. Fatigue occurs when there's too much load on the bearing. So, if you look at this equation, without going into all the nasty details, the fact is that if we increase the RPM that where we're operating the bearing, then we will reduce its life. But we can assume that we're running the bearing at a speed because that is what the bearing was intended to perform. So there's not much we can do in this area. However, where our focus needs to be is reducing the load. As we increase the load, we get this cube relationship here. So for example, if we double the load, we're increasing or reducing the life by a factor of 8, 2 to the power of 3. So these parasitic loads reduce the life of the bearing, and that is considered a cause of about 34% of bearing failures. In this animation, what we're trying to depict here is that because of unbalance or some sort of load variation, we get the load zone moving around the bearing. So instead of the load zone being in this area here and being as designed for that bearing, if the bearing was chosen correctly, instead we get this load that's moving around and drastically reducing the life of the bearing. In this case, if we've got a bent shaft or some source of vibration that's causing the inner race and the whole shaft to move back and forward, or if the bearing was cocked, then we reduce the life. If the bearing was not installed properly and the outer race was cocked slightly, you can imagine the additional load these rolling elements and therefore the raceways under. It's worth pointing out, we'll dwell on this a little bit more later in the presentation, but when we open a bearing, okay, we decide to replace the bearing, we take it out and we look at the raceway, you can see patterns on the raceway which tells you why the bearing failed. And if we saw a pattern like this, we can tell it's because of excessive load. So let's look at the next cause, lubrication. And in this case, we should point out we've got lubrication here as 36% and contamination, so contamination of the lubricant, as a separate cause. So the question is, is the lubricant that you are providing to the bearing the right lubricant? Is that lubricant, does it still have its additive pack and so on? Is there too much lubricant in the bearing? Is there too little lubricant in the bearing? Bottom line is, the bearings are designed to operate in a state where they are correctly lubricated, not too much heat and therefore not creating too much wear. In an ideal world, that lubricant is performing the function to reduce the contact between the rolling elements. Something that we could spend a lot of time discussing, but at this point where the rolling element is let's just say contacting the inner race, and the same up here, on the outer race, and same up here on the inner race, there are tremendous forces, because right at that point there, the lubricant is holding the rolling element away from the metal of the outer race. It is under tremendous pressure. In fact, the metal can deform because of that load, and the lubricant actually acts as a solid right at that point to keep those surfaces apart. If we were to travel right down and look as closely as we could at that point of contact, as we're doing here in the animation, those moving surfaces are being held apart by the lubricant. The surface of the metal, while it may seem smooth to the eye, microscopically there are all sorts of lumps and bumps and troughs and so on, as you can see here. And the point is, the lubricant has to keep those aspirations apart. So if it's not doing that, then of course there is wear. So looking at this gap between the rolling element and the raceway, the gap, or the fluid film, is just between 0.1 to 1 micron. A micron is a millionth of a meter, and approximately 0.039 mils, or thousandths of an inch. Now, to put that in perspective, a human hair is approximately 60 microns across. A dust particle, 25 microns. A fingerprint, if you were to just touch the bearing and look at the fingerprint, it's 12 microns. The smallest particle you can see is approximately 40 microns. So if you were looking at a lubricant and you could actually see particles, you know that those particles are approximately 40 microns in size or larger. Whereas at this point between the two surfaces, we only have approximately 1 micron, a 40th the size of the smallest particle that you can see. So therefore, the gap is very, very small, and it's important though that we maintain that gap between the surfaces. Now, what affects that gap? The load affects the fluid film thickness, heat affects the fluid film thickness, and the volume of lubricant affects the fluid film thickness. And obviously, as those two surfaces come closer together, we have this situation where there will be wear, and we will greatly reduce the life of the bearing. So we have to do everything we can to make sure the lubricant is able to do its job by reducing the load, by reducing the heat, and ensuring the correct volume of lubricant. Now, for a variety of reasons, we can get slippage on the raceways and skidding of the rolling elements if the lubricant is not right or if the bearing isn't properly designed for the application. And again, if we look at the rolling element bearings as we pull them out of the machine, then we can see not only a pattern on the raceways but also on the rolling elements. So this is very important. If we make those observations, we know why a bearing failed rather than just scrapping them and hoping that the bearing doesn't fail again in the future. Of course, some signs of lubrication problems are very obvious to see, but of course it's not good enough to just see them. You have to correct the situation. Okay, let's look at the next source of bearing failure: contamination. Contamination particles can damage the bearing surfaces. Contamination can cause oxidation of the bearing materials, the raceways and rolling element. So you need to consider how you store the lubricant, your practices involving machine washdown, the location of the machine and the location of the access to the oil sump and these sorts of things. You have to do everything possible to minimize the contamination of the lubricant. Now, again, we can look at the surface of the raceways and see signs of corrosion. In this particular case, you can see that when the machine has been stopped, water in the lubricant is separated and caused corrosion around the location of the rolling elements. You can see in a case like this, accessing the lubricant in such a dirty environment is bound to introduce particles. So the question is, what happens when those particles get into the lubricant? Well, if that particle happens to be small enough, but still larger than that 1 micron gap there, potentially what we can have is a situation where the particle, the rolling elements can roll over that particle, but there won't be damage. It'll flex and the metal will make allowance for that particle, but that's the best case scenario, I suppose. If the particle is any larger, then as the rolling elements roll over that particle, assuming they're not sort of pushed out of the way and sort of gouge through the metal, then we can have it sort of create the spall. Of course, then there's soft particles that can be sort of squashed by the rolling elements and they might get washed out of the lubricant. But so obviously we have to reduce the likelihood of contamination, and we have to test the lubricant, of course, to see if there is contamination. And last but not least, we'll look at the handling of the bearings and the installation practices. The fits and tolerances are critical. The use of proper tools and the correct training in the installation practices are critical. And transportation and storage of the bearings are so important, as I'll show you in a moment with one of the animations. So it's one of the problems, a very, very common problem in industry, that people involved with the craftspeople involved with installing the bearings may believe they are installing the bearings properly. They may believe also that it's more important to install the bearing quickly rather than taking the care to install it without damaging the bearing. Of course, they may not be aware at all that their installation practices could be damaging the bearing, or that any slight damage will be fine, that the bearing will survive any damage during the installation process. So it's all about providing training on the consequences of not installing the bearing properly and how to install the bearing properly. And from my own experience talking to people in this sort of role of training people, most craftspeople relish the opportunities to receive that training and to be given the time and the tools to do the job properly, to take pride in that role. Now, in this situation, if during the installation process the inner race was cocked on the shaft, then every single rotation of the shaft, you can see this wobble effect, if you like, and the rolling elements, you can just imagine what the additional load is on the raceways and the rolling elements. In this case, we're looking at false brinelling. Here we've got a machine that's operating, and the transparent one closest to us is not operating, so it's in standby mode. Well, while that machine is operating, it's causing the bearing to vibrate, and because it's not turning, we've got this this chipping away at the raceways. Now that can happen for a few reasons. It can happen while the bearing's being transported. It can happen while the bearing's sitting there in the stores. There are ways that you can deal with this process, just alternating more frequently between Unit A and Unit B, turning the shaft, turning the bearings when they're being stored. There's a lot you can do about these things. Point is, you've got to be aware that they are problems in the first place. And of course, during the installation process, if a hammer is used to force the bearing into place, then all sorts of damage can be done. Now these examples, that example is certainly a little more extreme, but even in this case you can see where the rollers have sort of damaged the raceway. So the training and the tools need to be provided so that the bearing can be installed correctly. So now we have an idea of why the bearings fail. Let's have a look at the condition monitoring technologies in brief and the idea of condition-based maintenance. Condition monitoring can do a lot to improve the reliability and reduce the likelihood of failure. The first thing we can do is use condition monitoring techniques to replace the lubricant based on condition. So rather than based on a certain number of running hours of the machine, we replace it on condition. So we look for contamination, we look at the chemistry of the lubricant, the viscosity, the acidity, and all these sorts of properties to make sure that it is still able to do its job properly. And then we can look at replacing the bearing itself based on condition. We can look for the telltale signs of wear particles, we can look at the vibration patterns, we can listen to it with ultrasound, we can even look at it with thermography and see a temperature increase. That's going to happen much later in its life, but still we can use these technologies. Now, particularly when we look at this here, what we are doing is we are waiting for the damage to occur. We're detecting that the damage has occurred. We're seeing that the life of the bearing has been greatly reduced and that it may fail soon, and we're avoiding that catastrophic failure. Avoiding the failure is great, but it's not the end goal here, which we'll talk more about in a moment. So just looking at the vibration, there are lots of ways we can use vibration to solve this problem. Firstly, we can use vibration to detect the issues that will cause bearing failure. So we can use vibration and ultrasound to look for signs of poor lubrication. We can look for fluting or EDM, where there's a current being passed through the bearing which leaves a pattern on the bearing, a type of wear pattern. We can look for signs of cocked bearing, as I illustrated before, where the inner race is cocked on the shaft or the outer race is cocked in the housing. We can detect with vibration the situation where there is skidding and sliding. Either the whole bearing is turning in the housing, or the rolling elements, instead of rolling, are at certain times actually skidding and sliding inside the bearing. We can also detect faults that will result in bearing damage: unbalance, misalignment, looseness, resonance problems, and so on. So at this stage, with an unbalanced machine, the bearings may be in good shape, but if you leave the machine out of balance, the excessive load that we are adding to the bearing will reduce its life, so later we'll detect the problem. Now, the good news is that we can understand the type of vibration that's generated by the bearings when there is a failure condition, and therefore if we apply the technology correctly, we can detect the fault at an early stage. The earlier we learn that there's a problem, the more time we have to react to it. Now, yes, we are reacting to it, but at least we can decide what parts we have, what labour we require, what downtime we have already planned, what our production demands are, and all sorts of things. So in this particular case, I'll just make the animation go again. If there was damage on the outer race, then as each one of these rolling elements rolls along and comes into contact with that particular point on the bearing, we get this ping of vibration, and that's something that we can detect. So if we look at how bearings do vibrate, I'll just bring up a little simulator here. This just helps describe how bearings work. Again, if I've got my damage on the outer race here, then as the shaft turns we get the sort of the normal, and we're just simplifying the view here. We've got this normal vibration due to the turning of the shaft and any unbalance, but just when the fault is not very severe, we have these little pings of vibration. Now, at the early stage, it would be impossible to see that small ping of vibration, but we can use techniques that are sensitive enough to detect it. As the fault gets worse, then that ping of vibration, the amount of damage here is greater, and therefore we get stronger vibration. But there are techniques we can use to isolate the bearing vibration, to just focus in on the bearing, and then treat it in a certain way called enveloping or demodulation. And there are other special techniques, peak view, shock pulse, and so on, that can isolate the bearing vibration and allow us to detect the fault at an early stage. So let's look at that. You've just seen how the bearings vibrate, and that they emit this high frequency vibration initially, and then as the problem gets worse, it's easier to detect it at a lower frequency that you can hear with your ear. In the really late stage, you can hear it. So the question is, how are you going to go about detecting those faults? Now, there are some very sophisticated tools that we'll mention in a moment, but there are some simpler tools, some tools that allow us to hear that vibration. So for example, ultrasound allows us to take the very, very high frequency vibration that's well beyond our natural ability to hear, and it transforms that vibration down to a lower frequency that we can hear. So you can listen to the vibration, you can get readouts, and there are a variety of tools like this that are available. The nice thing about this is that operators can use these tools, and between the routine tests with the full spectrum analysis system, for example, operators can be checking bearings more frequently and alert the condition monitoring team that an additional test is required. But these tests are fairly simple, but they certainly have their role, and they can detect other faults beyond just bearing faults. In this particular case, if a bearing was not properly lubricated, for example, we get a lot of sort of noisy, high frequency vibration. But we can actually listen to the bearing as it's being lubricated. So the before sound, hopefully you can hear this. And then when it is lubricated, you can hear the sound is much smoother. So that's a tool that we can use to just listen to the bearings and determine the lubrication state, and we can listen to the bearings while performing the lubrication task to make sure that the lubricant is actually getting into the bearing. So there are lots of tools that can be easily used, not very expensive, that give you a readout of the amplitudes. They can be trended, and they give you an idea of what's going on. With oil analysis, of course, we can determine the condition of the lubricant. We can look at the viscosity, acidity, alkalinity, the various additives. We can detect contamination, the water, particles, chemicals, and we can detect the particles specifically through particle counting. We can look at elemental analysis, look at the actual metallic elements and organic elements to see what's going on. It's worth mentioning, though, that conventional oil analysis cannot detect particles greater than 10 microns in size. So, I'll mention wear particle analysis in just a moment. So just to give you a brief idea, it's a very important tool to use, particularly on your more critical machines, to make sure that the lubricant itself is okay and that there's no contamination. If we perform wear particle analysis, we can actually look closely under a microscope at the lubricant to see if there are signs of wear. Now, large particles like this allow an analyst to determine the type of metal and the nature of the wear that's taking place. Cutting wear and other sorts of wear that have characteristic shapes and colours. So we can, a trained eye can tell what sort of particle that is, and because of its shape, how that particle came to be, whether it's been rolled through by the bearings, whether there was skidding involved, whether there was heat involved, and so on. So these sorts of techniques can also test, if there's dirt, in effect, silicates in the lubricant. Of course, we can use thermography as well. I mentioned earlier that that's only going to be effective in the later stages, much later stages of the bearing failure. Long before the bearing gets hot, we will see particles, we will see changes in the vibration, we'll be able to hear it with ultrasound. But still, it's an important technique to use in addition to the other technologies. Of course, this is just an attempt at humour. Sometimes it is easier to see that bearings are hot, but hopefully you don't see this very frequently. Okay, and then we can utilize advanced vibration techniques. We can use spectrum analyzers to detect the faults, both at an early stage and a later stage. The good news about rolling element bearings is that they generate characteristic frequencies. There is a frequency related to the time it takes for the cage to make one revolution around the bearing. There's a characteristic frequency that relates to damage on the outer race, and if you watch there, you can see how often those pings of vibration are occurring. In this case, the rolling element itself is damaged, and as it rolls along, potentially that damaged area contacts the inner race and outer race, and we can see there's a different frequency being generated. The periodicity or the timing between those pings of vibration is different to what it was on the outer race, and on the inner race those pings of vibration are a different frequency again. So the good news is we can use analysis techniques to detect all of those things. Now we looked at the simulator just before and we could see those pings of vibration. We could go into that in a lot more depth, but we have other presentations on that topic. The point is at this stage that the vibration generated as a bearing fails changes over the lifetime of the bearing. Initially, when the bearing is in good condition and is properly lubricated, we don't expect to see any vibration that is unique to the bearing. But if there's a lubrication problem, or there's very slight bearing wear, or a spool is starting to develop, it generates very high frequency vibration. But these techniques here are all designed to pick up those telltale signs. The techniques listed down below will not be effective at the very, very earliest stages of the bearing wear. Now, we may be able to detect the signs of a bearing fault a year or more ahead of time, a year before the bearing has to be replaced. Now it all depends on circumstances, the speed and load. If a bearing is in an application where it's high speed and high load, the failure will occur more quickly than if it's lower speed and lower load. But these techniques are utilized to detect a bearing fault at the earliest possible stage. As the fault develops, we can use additional techniques. The acceleration spectrum, for example. This I've placed enveloping and demodulation in this high frequency versus very high frequency. It's debatable which one it belongs in. It just depends on the particular method that your analyzer utilizes. And then as the fault develops, we can utilize the velocity spectrum. Time waveform analysis can be used in this area as well, but certainly the overall level vibration just with a simple handheld meter giving you the vibration in inches per second or millimeters per second is something that you wouldn't want to rely on, because it takes, the bearing has to wear quite a lot before you will detect it with that technology. So it's important to understand what each technology does, how it basically works, and where it's most effective. Okay, so we can utilize all those great techniques to check the lubricant, to look for telltale signs of the bearing wear. We can use very simple techniques and we can use more advanced techniques. But what more can be done about the bearing failures? Well, I guess the goal should be, don't just detect the faults, try and eliminate them. So avoiding that catastrophic failure is important. There's the personal injury issues and the environmental harm that might occur. There's the downtime, secondary or collateral damage that can occur when a bearing fails. There's overtime labour and all sorts of reasons. That's important, but detecting the fault does not improve reliability. Yes, we might detect a bearing that fails every 3 months or so, and it's great that it doesn't fail. I mean, it may fail every 3 months, it may fail every 3 years. Ultimately, we want that bearing to last its design lifetime, not a shorter period of time. Just detecting that there's a problem does not actually extend its life. It just reduces the consequences. So, how do we improve the reliability of the bearings? Well, that's where this precision or proactive maintenance comes into it. Techniques that can actively reduce the likelihood of bearing failures, thus improving their reliability. So, what you have to consider is all the reasons why bearings fail. Poor design, not only of the bearing itself, but the selection of the bearing in the machine, or the design of the machine itself. The purchasing process, the transportation of the bearings, the storage of the bearings, the installation of the bearings, the lubrication, the way we're operating the machine, poor maintenance, and so on, all reduce the bearing life. So the question is, what are you going to do about it? You recognize that all of these reasons reduce the life of the bearing, so what can you do? Now, we could spend a long time talking about this particular part, this reliability spectrum, as I call it. The bottom line is that, number one, when machines are being purchased, and when decisions are being made about who will overhaul a machine and who will balance a machine and these sorts of decisions, unfortunately a lot of organizations reward the purchasing department for choosing the least expensive supplier of that equipment. And the design process is all about the actual function that it has to perform, rather than the maintainability and reliability of the machine. The fact is that in a lot of cases we are purchasing problems right here. We are purchasing equipment and choosing suppliers based on a very short-term criteria of upfront cost rather than lifetime cost. So changes need to be made here. But even with that perhaps flawed purchasing process, nothing is being done to test the machines as they come in to make sure that they're actually in good condition. We purchase a motor, it may already have problems. Now, it might seem strange. You think, wait a minute, I'm buying a motor from a respected supplier, surely it's in good condition. Unfortunately, many organizations have looked at this in depth and found that they are often buying equipment that have problems. They may resonate when they operate, they may have bearings installed incorrectly, or all kinds of issues. So the point is that if during this specification process you also define an acceptance testing criteria, which says, I will not accept lubricants with a particle count above a certain limit, for example. I will not accept balance jobs that don't meet this ISO standard. I will not accept motors or pumps or fans or compressors that have vibration at specific frequencies that is higher than a preset amount. There are lots and lots of things you can do with acceptance testing to ensure that the equipment that you ultimately install in your plant is in the best possible condition it can be. And if it's not, you don't accept it. Someone else will probably receive that motor that you've rejected, but you don't accept it and you don't start paying. You may delay the payments, you certainly delay the commencement of the warranty period and so on until that's done. But then we can take it a step further and we can say, alright, we will check, for example, when we're buying new equipment or making modifications to plant or whatever, we will always check that there is no resonance. We'll make sure that machines are balanced and machines are aligned. We won't take vibration readings and wait until we see a balance condition or a misalignment condition. We will proactively precision balance, precision align, and perform tests to ensure there is no resonance going on. Along with all of that, we will step back and we will look at the equipment and consider what the failure modes are. This does not have to be a long, extended, navel-gazing process that doesn't have any results in the end. Most people who work with machines in your plant will have a pretty good idea of what the failure modes are, and therefore, based on that, you can decide, well, what sort of condition monitoring tests do we need, and how frequently do we need to take those measurements. It's no point using condition monitoring techniques that don't match the type of failure modes that you actually experience. Then we'll go ahead and we'll take care of the lubrication, as I've mentioned. We'll perform condition monitoring, but not just doing bearing analysis. There are a lot of plants that put all their focus on just detecting the bearing faults themselves. We need to use the full capabilities of vibration analysis to detect and correct the unbalance, misalignment, bent shaft, and other sorts of faults that will wear out the bearings. And then we need to utilize other condition monitoring technologies that will tell us that the lubricant has particles, or the lubricant's not doing its job, or etc., etc., other condition monitoring technologies. Report generation is critically important, but not the emphasis of this particular discussion, but performing root cause failure analysis. Even if we do all these steps that we've looked at here, machines will ultimately fail. But whatever the situation is, we need to look at the root cause of any failure and say, well, is there something we could do to avoid this problem occurring in the future? Is there some training we need to provide certain people? Is there some changes we can make to our purchasing process, or do we need to change the acceptance testing criteria? Do we need to use better guidelines on our balance and alignment procedures? What is it we need to do? If we perform that analysis and we take the action as a result of what we learn, then we will be improving the reliability of the bearings. So let's have a look at some of those techniques. As I've mentioned, unbalance is a killer of bearings. If you can imagine, in this very simple and exaggerated case, if a fan was out of balance and you could run it out in space, well, it would rotate in that circular motion. But of course, you're not out in space, you've got this machine tied down. Well, those bearings and the support all have to take those rotational forces, and therefore those bearings are being pounded all day long. And you saw earlier the impact of increasing load on bearing. We drastically reduced the life. But the solution, we can perform in situ balancing. We can take vibration readings on the machine and determine how to correct the balance, and in some cases we need to take the rotor away to be shop balanced. But the problem is solvable. We can look at the reason for the machine becoming out of balance. Maybe there's dirt getting into the airstream or whatever it is, but ultimately we need to run machines that are properly balanced. If you consider misalignment, in this case just offset or parallel misalignment, we've got these forces, and again, for the sake of the animation, we've got the two components moving in space, but if we tie those down, you can imagine the forces on the bearings, on the couplings themselves, on the shafts, the seals, the bearings, and the structure as a whole. So we need to eliminate that extra force. But we can use lasers, we can use dial indicators to precision align the machine, greatly reducing those forces. Likewise with belt-driven machines, we have to make sure there is no offset between the pulleys, that there's no angle between the two pulleys. We need to make sure that the belt tension is correct, that there's no wear and so on. So all of those things will increase the life of the bearings and increase the life of the machine itself. Resonance is a topic that's hard to summarize. All I can say is that when a machine generates vibration, if it happens to coincide with something called a natural frequency, the machine will vibrate much more. There will be much greater movement, and that movement puts the stress on the bearings and on other parts of the machine. There are tests we can do to check if this is the case, and there are techniques we can use to correct the problem. It may be something you haven't heard of before. It may be something you're quite familiar with. The point is, it is very common. It is very common for machines to be running near natural frequencies, or that one of the sources of vibration from the machine, the pump vane rate for example, or the bearing frequencies themselves, or other frequencies, excite these natural frequencies, increasing the vibration amplitude. So we need to reduce that, or eliminate it if possible. As we've already discussed, we can look at the bearing installation practices and make sure that we don't have cocked bearings, that we don't have false brinelling, we don't have brinelling as the bearing is hammered into place. All these sorts of issues need to be eliminated. If we install the bearing properly, we'll have a much better situation. We need to look at the lubricants. We need to remove water, we need to lubricate it properly, we need to filter the lubricants, we need to store the lubricant so that we make sure that it's not contaminated in the storage process, and that the correct lubricant is applied to the correct machine in the correct way. All of these things, it's not rocket science. There's plenty of documented ways on how to do it. There's products that can help you and consultants that can help you. It just takes that commitment to doing it properly and a recognition of how important it is. So, how do you make all these changes? We've talked about a lot of things which you may not be doing right now, and you may think, oh, it all sounds great, but boy, we're always so busy. Well, there is a lot that can be said on this topic, and in this presentation we're just summarizing these various areas. The key really is in the people. The key is that everyone, from the top to the bottom, however you measure the top and the bottom, every person who is involved with the operation, maintenance, reliability, the top management and so on, everyone has to look at reliability as being critically important. People have to be trained to do the lubrication and install the bearings and do everything else correctly. People who operate the machines need to understand that if they don't operate them correctly, they are reducing the life of the machines. When there is shutdown for any reason, rather than rushing the machine back into service, tasks like precision alignment have to go ahead, and other tasks which may be a little bit time consuming and may mean the plant is shut down for just that little bit longer. The point is that it will keep running, the plant will keep running for a lot longer because you've taken those preemptive steps. So without providing the support to people, the education to people, and just everyone being on the same page with reliability, it makes a huge difference. And all I can say is you can visit some plants and everyone's in firefighting mode. Everyone's dealing with the next problem. There's finger pointing. There are sometimes accidents. It's a not necessarily a very enjoyable place to work. On the other hand, you can go to other plants where everything runs like clockwork, where everyone treats their machines as they would, a valuable car or something like that. It's like, oh gee, we will take care of these machines and they will take care of us. They feel safer working, there's less stress, they're not being called out in the middle of the night and all these sorts of things, and their plant is running at full capacity, and therefore the company is more profitable. If there's comparisons going on between plants, then your plant will be looked at positively. So there's lots of other steps you can go through to make sure that you are taking care of the machines, but we've talked about a lot of those points. But if you don't have the people issues solved, forget about all those other things, because when the crunch time comes, people won't balance it properly because they won't have been trained, or they won't see the importance. They won't align the machines at all, or they'll align them poorly. And we can go through example after example. You can say what you like. You can go out and buy whatever test equipment and laser alignment systems. You can do whatever you like. You can't throw money at this. You have to throw people who have the right motivations and incentive. The results, everyone's happy. As I say, if you're working in a plant where people are taking pride in their work, where they're achieving good results, where they feel safe from injury, but also safe from the plant being shut down and layoffs and all these sorts of things, as managers try to find other ways to save money, it is a much better environment. Okay, well, that concludes this presentation. I sure hope you found it useful. You can see my email address there if you want to ask questions specifically about this presentation, but otherwise please email learn@mobiusinstitute.com if you have any sales inquiries about our courses and variety of products and all sorts of things that we offer. We offer courses all over the world. We probably give more training by far in vibration than in other areas, but still, if you're interested, visit our website or email learn@mobiusinstitute.com, and of course there are lots of presentations like this on our website. Thanks for taking the time to view this presentation. I hope you found it useful.